Have you ever stopped to think about what's really powering the AI revolution? I mean, what are the hidden engines making it all possible? Well, today we're going to pull back the curtain on exactly that: machine learning frameworks. These are the tools that took AI from just an idea in a lab to the world-changing technology we see today. So let's get into it and see what's really running the show. Okay, so it really all comes down to this one central question. You have an AI model, and it's supposed to get smarter. It does that by tweaking millions, sometimes billions, of tiny internal knobs or parameters. But how in the world does it know which way to turn them? That's the core mystery we're going to unravel today. And this is pretty much the magic spell. This one little command, loss.backward, it looks so simple, right? But when a developer types this, it kicks off this incredible cascade of ridiculously complex calculations. This is what makes modern AI work. But what is actually happening inside this one-line miracle? To really appreciate just how amazing that one line of code is, you have to think about the alternative. Imagine trying to build a deep learning model completely from scratch with no framework to help you. It's a massive undertaking. You'd be stuck manually coding hundreds of lines of really tricky calculus and matrix math, and that's just for a simple network.
And the scale we're talking about here is just mind-boggling. Training a big, modern language model means coordinating billions of floating-point operations. Trying to do that from scratch, it isn't just hard. For pretty much everyone, it's economically impossible. You just couldn't afford the time or the compute power.
So, how do we bridge that gap? How do we get from billions of messy, complicated operations all the way down to that one, clean, simple command? Well, that's exactly where frameworks come into play. The best way to think about them is as the operating system for artificial intelligence. And yeah, that's really their whole job. They handle all the messy, low-level stuff, all the calculus, all the optimizing for the hardware, making it run on multiple machines. They take care of all of it. This frees up developers to focus on the fun part, being creative and building the next generation of incredible AI models. So let's dive into the first secret ingredient that makes all this work. At the very heart of every single machine learning framework is a concept called the computational graph. You can think of it as the master blueprint that maps out every single calculation the AI needs to make, step by step. So what that means is, before a single number is crunched, the framework draws up this incredibly detailed plan. Every little circle, or node, is a math operation, like addition or multiplication, and the lines, or edges, show how the data flows from one operation to the next. So to the framework, your complex AI model just looks like this neat, organized map of operations. Now here's where it gets interesting. Not all of these blueprints are made the same way. For years, there was this huge debate raging in the AI world. It was almost like a philosophical war over the absolute best way to build these computational graphs. It really came down to two camps. On one side, you had static graphs. I like to call these the architects. They meticulously plan out the entire computation map before anything actually runs. And on the other side, you have dynamic graphs. Let's call them the improvisers, which build the plan on the fly, piece by piece as the code is running. And this table just lays out the trade-offs perfectly. Static graphs, the architects, because they see the whole plan up front, can do these massive optimizations. That makes them super efficient and great for production systems where every millisecond counts. But the dynamic graphs, the improvisers, are way more flexible and so much easier to debug, which is exactly why they became the favorite tool for researchers who are constantly experimenting. Okay, so we've got the blueprint, the computational graph. But what's the engine that actually powers the learning? This brings us to our second big secret, a brilliant mathematical trick called automatic differentiation. This is the absolute genius that automates the single hardest part of machine learning. Let's go back to our core problem, right? For a model to learn, it has to figure out something called the gradient for every single one of its millions of parameters. A gradient is just a term from calculus for the rate of change. Calculating all of them is a gigantic and traditionally a very, very difficult math problem. So frameworks solve this with this really elegant two-step process. First, in what's called the forward pass, they just run all the calculations. And as they do it, they build that blueprint, that computational graph, and they remember every single operation along the way. Then, when that magic loss.backward commands that's called, they kick off the backward pass. They literally just trace that blueprint in reverse, and by applying a calculus rule called the chain rule at each step, they can automatically and super efficiently calculate all those millions of gradients. It's amazing.
But look, even with all these brilliant software tricks, the AI boom just wouldn't have happened without the final piece of this puzzle, a huge leap forward in raw hardware power. The software and the hardware really evolved together, each one pushing the other to be better.
You can really see it in this timeline. There was just this explosion of new ideas in the 2010s. It kicked off with Theano back in 2007, which was one of the first to really use GPUs. Then you had Google's TensorFlow, which was built for massive distributed scale, and that was challenged by Facebook's PyTorch, which really championed those flexible, researcher-friendly dynamic graphs. Each one was standing on the shoulders of the ones that came before.
You know, the introduction of GPUs was the real game changer here. And why is that? Well, it turns out that deep learning, at its core, is just doing massive, massive amounts of matrix multiplications over and over again. And GPUs, which were originally designed for video game graphics, just happen to be unbelievably good at doing thousands of those kinds of calculations all at the same time, in parallel.
The impact was just unbelievable. For these specific tasks, using a GPU gave you a 10 to 100 times speed up over a normal CPU. Now, this wasn't just a small improvement, this was a fundamental shift. It's what made training these truly giant models actually practical for the first time.
So what does that look like today? Well, how about 312 teraflops? That's 312 trillion calculations per second from a single modern NVIDIA A100 GPU. This is the insane amount of computational power that today's frameworks are designed to command.
So when you put it all together, the whole picture becomes clear. Frameworks are that crucial layer that hide all the insane complexity, making modern AI usable. They use computational graphs as their blueprint, they use automatic differentiation as the learning engine, and they harness the incredible power of specialized hardware like GPUs to make it all happen at lightning speed. This constant dance between more powerful frameworks and even faster hardware is what's pushing the boundaries of what AI can do every single day. And as these tools get even more powerful, even easier to use, it really makes you wonder, right? What totally new forms of intelligence are we going to unlock next?